Okay, so we eventually came to the culmination of our course, namely to the spectral theorem for bounded self-adjoint operators on a Hilbert space. In fact, the spectral theorem is not a theorem in the usual sense of the word. It's rather a collection of results which are closely related to each other and which tell us something important about the structure of normal operators. Some people say that different forms of the spectral theorem are equivalent, or at least essentially equivalent to each other. In my view, this is not exactly the case. Usually the process of deducing one form of the spectral theorem from another one is not always automatic, is not always immediate, and of course is by no means automatic. So in summary, there are different forms. There are several different forms of the spectral theorem. They are very useful. They are closely related to each other, but they are not equivalent, at least formally. So today we will discuss one of the forms of the spectral theorem, namely spectral theorem in terms of functional modules. Let's call it Spectral Theorem One. Theorem on functional modules. Well, to understand better what the result is about, let's start with some motivation. First of all, suppose that we have a self-adjoint operator, T, on a finite dimensional Hilbert space. In this case, we have a well-known theorem from linear algebra, which states that T is diagonalizable, in the sense that there is an orthonormal basis in H such that the matrix of T in this basis is diagonal. Equivalently, this means that we can draw the following commutative diagram. There is a unitary isomorphism between H and Cn, where of course n is the dimension of n of H. Isomorphism U, a unitary isomorphism, which gives us a unitary equivalence between T and an operator given by a diagonal matrix. So this means precisely that T is diagonalizable. And the choice of U is equivalent to the choice of an orthonormal basis. Okay, and let's now recall another also well-known result, which was proved in our course, at the beginning of our course, namely the Hilbert-Schmidt theorem. Namely, suppose now that T is a compact self-adjoint operator on an infinite dimensional separable Hilbert space H. Infinite dimensional and separable. So the Hilbert-Schmidt theorem implies that there is a unitary isomorphism between H and the little space, isomorphism U, which gives us a unitary equivalence between our operator T and the diagonal operator m lambda, which acts on the little space. So m lambda is the corresponding diagonal operator. So what we're going to do is to extend these results to an arbitrary self-adjoint, and in fact not necessarily self-adjoint, but an arbitrary normal operator on a Hilbert space. So suppose that, well, we suppose for simplicity that T is self-adjoint. And H is an arbitrary Hilbert space. It turns out that in this case, we can always find a measure space, omega, and a unitary isomorphism between H and the respective L2 space, such that U establishes a unitary equivalence between our operator T, this is T, and the multiplication operator, M phi, by a bounded measurable function phi. And phi is just the multiplication operator. So this is the first two columns is our motivation, and this is our goal. This is what we are going to prove. By the way, let's observe that in a special case where omega is countable and mu is the counting measure, we get this picture. And in a special case where omega is finite and mu is the counting measure, we get this one. So the spectral theorem, in terms of functional modules, generalizes both the Hilbert-Schmidt theorem and the well-known statement from linear algebra, from finite dimensional linear algebra. Yeah.
In the Hilbert-Schmidt theorem, we also know that lambda is from vanishes at infinity.
Yeah.
There is no analog for this in the spectral theorem.
The fact that lambda goes to infinity is, if we already know that T is unitarily equivalent to a diagonal operator, then the fact that lambda goes to infinity, lambda vanishes at infinity, is equivalent to the compactness of T. So in the general case, if we already know that T is compact, then we just come back to the second column, to the Hilbert-Schmidt theorem.
From the general spectral theorem, we can conclude this result for any self-adjoint operator, not necessarily compact.
No. Assuming, if we assume that it is compact, then we come back to the Hilbert-Schmidt theorem. If it is not compact, then we cannot claim that it is diagonalizable. It is not necessarily equivalent to the diagonal operator. It is a more general statement. If you take an arbitrary operator of this form, in general, it can happen that this operator has no eigenvalues at all. So there is no hope to represent this operator in this term. So this is a very special case. This picture is a very special case of this one. If it is compact, then of course we can write the diagonal form, but if it is not compact, then in general we can say nothing about the point spectrum. So in other words, the point spectrum can be empty. And the most basic example is the multiplication operator on the big L2 space on the interval. If you take the interval 0, 1, and the operator which takes f to Tf of t, the multiplication by the coordinate on the big L2 space, then this operator, of course, is self-adjoint and bounded, but it is not diagonalizable, and its point spectrum is empty. There are no eigenvectors at all. And so then this is more or less typical.
What have you said about this method?
U is a unitary isomorphism. It means that it is bijective and preserves the inner product. Bijective and preserves the inner product. Okay, so this is our goal. And more exactly, we are going to prove a slightly more general statement about the presentations of commutative C-star algebras, and then to deduce the spectral theorem as a special case. So let's introduce some terminology. Suppose that A is the Banach star algebra, and H is a Hilbert space. By definition, a star representation of A on H is a star homomorphism pi from A to the algebra of bounded operators on H. By the way, let's recall that since V of H is a C-star algebra, it follows automatically that, before we recall it, let's adopt the convention that everything is unital. So we always assume that A is unital, and pi takes the identity of A to the identity operator. So pi is a unital star homomorphism. And let's recall that in this case, we know that pi is automatically bounded, and the norm of pi is less than or equal to 1. So some time ago, we proved that each unital star homomorphism from a Banach star algebra to a C-star algebra satisfies this condition. Let's now introduce another notion, which is in fact equivalent to the notion of a star representation, but which is sometimes more convenient. We define a star module over A to be a Hilbert space, is a Hilbert space H, together with a left A module structure such that the following two conditions are satisfied. First of all, we require that the action of A on H is continuous. This map, which takes each pair A and V to AV, is continuous. And second, the inner product on H should be compatible with the involution on A in the sense that the following formula holds. The inner product of AV and W equals the inner product of V and A star W for all A in A and V and W in H. Again, we'll adopt the convention that A is unital and that the identity of A acts as the identity transformation, which is quite common in algebra. The identity of the algebra acts identically. Okay, let's now observe that, in fact, there is a one-to-one correspondence between our representations, star representations, and star modules. There is a one-to-one correspondence between the collection of all star representations of A and the collection of all star modules over A. More exactly, if we have a star representation pi, then we can define an A module structure on H by the following formula. We take the operator pi away and act on V. And the other way around, if we have if H is a star module over A, then we read the same formula right to left, and we see that this formula determines a star representation. In particular, condition 2 here is equivalent to the fact that pi is a star homomorphism. Not just a homomorphism, but it preserves the involution. So this is our first observation. And observation 2 is that if H is a star module over A, then we have the following inequality. Well, indeed, this inequality follows from the fact that the norm of each star representation, pi, is less than or equal to 1. Okay. By the way, it's a nice exercise to show that actually condition 2 implies condition 1. That is, the continuity is automatic from this condition on the involution. This is a nice application of one of the fundamental principles of functional analysis. This was a hint. Okay. Let's now introduce morphisms between star modules. Suppose that we have two star modules, H1 and H2, star modules over A. Then we say that map phi from H1 to H2 is a morphism of A modules. If it is a bounded linear map, F is a bounded linear operator, and a module morphism, so it respects the action of the algebra in the following sense. So a morphism of star modules is just a continuous A module homomorphism. In particular, we say that phi is a unitary isomorphism. A unitary isomorphism. A unitary isomorphism is an A-module morphism which is a unitary operator. Unitary means bijective and preserves the inner product. And we say that H1 and H2 are unitarily isomorphic, and write the following symbol. Unitarily isomorphic. If there is a unitary isomorphism from H1 to H2. Let's now introduce an important special class of star modules. Namely, let's define cyclic modules. Suppose that H is a star module over A. And as before, A is unital Banach star algebra. And suppose that V is an element in H. We define the cyclic submodule, of H generated by V as follows. So this is the submodule of H denoted like this. And by definition, this is the closure of all elements of the following theorem in H. So it's easy to see from the definition that this is indeed a closed submodule of H, and in fact this is the smallest closed submodule which contains the vector V. We say that H is cyclic if there is a vector V in H such that the cyclic submodule generated by V equals H. And each such vector V is called a cyclic vector. Let's now look at two important examples. Example 1. Suppose that X is a compact Hausdorff topological space. And suppose that mu is a positive Radon measure on X. First of all, let's observe that L2, the big L2 space on X, is a star module over C of X, over the algebra of continuous functions on X. And the action of this algebra on the space is just the pointwise multiplication. So this is a star module, and let's now observe that it is cyclic. Namely, if we take the function which is identically 1, and consider this function as an element of the L2 space, well, it is indeed in the L2 space because our measure is assumed to be finite, then this is a cyclic vector. So we see that this is a cyclic module. And why is it a cyclic vector? Well, if we look at the definition, we see that if we look at this submodule before we take the closure, we get just the canonical image of C of X in L2 of X. And we discussed in the previous lecture that for each positive finite Radon measure, this subspace is dense in L2 of X. So this is a cyclic vector. Okay, now example 2. Which is more general than example 1. But which is not always cyclic. Example 2. Suppose that we have an arbitrary measure of space, omega, a mu, an arbitrary measure of space, not necessarily finite. And actually not necessarily sigma finite, an arbitrary measure space. And observe that L2 of omega becomes a star module over the algebra L infinity omega. Again, with respect to the pointwise multiplication. Suppose now that X is a compact Hausdorff topological space. And suppose that we have a measurable map, phi, from omega to X. where we consider X as a measurable space with respect to the Borel sigma algebra. So phi is a measurable map. Observe now that phi induces a star homomorphism, phi dot, from the algebra of continuous functions on X to the algebra bigger infinity of omega. And this homomorphism phi dot is just the composition with phi. So this is a star homomorphism. So we have two star algebras, this one and this one, a star homomorphism computed here, and a star module over the second algebra. So we can, this homomorphism enables us to consider L2 as a star module over this algebra. L2 of omega becomes a star module over C of X. And explicitly, the action is given by the following formula. AF is the pointwise product of phi dot of A and F. Here A is a continuous function, and F is an element in L2 of omega. Let's denote this module. Introduce a special notation for this module. This module will be denoted by L2 omega mu phi. So the module structure is determined by the measurable map phi. So obviously example 1 is a special case of example 2, namely if mu is the measure from example 1, we can just take the identity map from X to itself. So phi is the identity map from X to itself, and we get, so this module becomes the module from example 1. But I don't claim that this module is cyclic. In general, this is not the case. So now our next goal will consist of actually two results. The first result states that each cyclic star module over C of X has this form, has the form described in example 1. And the second result will be that an arbitrary, not necessarily cyclic, star module over C of X has this form for a suitable measure space and for a suitable measurable map. And essentially, this is exactly the spectral theorem for representations of C of X. So, Theorem One, which gives us a functional model for cyclic star representations of C of X. Suppose that X is a compact Hausdorff topological space. And suppose that H is a cyclic star module over C of X. I claim that there exists a positive Radon measure, mu, a positive Radon measure mu on X, such that H is unitarily equivalent, unitarily isomorphic as a star module to L2 X mu, unitarily isomorphic over C of X. So in other words, each cyclic star module is described by our example 1. Yeah. If x is one point, then C of x is just the complex numbers. So in this case, the theorem states that just states that each Hilbert space is which is a cyclic over the complex numbers. So what is a Hilbert space, which is a cyclic module? Is one-dimensional. So in this case, this is true, but this is kind of trivial result. Okay, so first of all, we construct mu. The existence of mu will follow from the Riesz-Markov-Kokutanya theorem. Namely, first of all, we choose a cyclic vector, V, a cyclic vector, and we apply the Riesz-Markov-Kokutanya theorem, whose statement of the theorem was given at the previous lecture. This theorem gives us a Radon measure, a complex Radon measure mu, such that the following identity holds. If f is a continuous function on x, then this formula gives us a bounded linear functional on C of x. And we know that a bounded linear functional is given by a measure, is given as an integral with respect to a measure for each f in C of x. And let's now show that this is exactly the measure we are looking for. First of all, we have to show that mu is positive. Well, why is it positive? So we suppose that now that f is a positive function, non-negative function on x. And we can take the square root of f. F equals g squared, where g is also positive. And we substitute f here. So the integral of f, yeah.
Is it f is real value?
Of course. Well, when I say that a complex number is non-negative, I mean that it is real and non-negative. And the same assumption, the same convention that applies to functions. We say that a complex valued function is non-negative if it is real and non-negative. So now the integral of f is this inner product. So we substitute g squared here. And now we use one of the axioms of star module. G is real, so we take one copy of g from here to here. And we move it to the second factor. But this inner product is non-negative. And so we see that our measure has the property that the integral of each non-negative continuous function with respect to mu is non-negative. It's a simple exercise in measure theory to show that this implies that mu is a positive measure. Okay, let's now construct this isomorphism. So let's introduce some notation. For each continuous function f on x, let's denote by the following symbol, f in square brackets, the equivalence class of f in the L2 space. The equivalence class of f in L2 of x. And let's now denote by E the set of all such equivalence classes where f runs over C of x. So this is a vector subspace in L2 of x. And moreover, this is a dense submodule. dense COX submodule of L2 of X mu. For any positive radon measure, yeah. The density was discussed in the previous lecture. This follows, this is more or less a corollary of Urson's lemma. Yeah, the Risk-Markov Kakutani theorem always gives us a radon measure, in general, a complex radon measure, but we have just proved that it is positive. Okay, so this is a dense COX submodule. And let's first of all, to construct our isomorphism, we first of all construct a morphism. So we want an isomorphism between these two modules. So as a first step, we construct a morphism from E to H. And to construct such a morphism, let's first of all do a little calculation. So we take two functions, two continuous functions, f and g, and let's look at the following inner product, fv and gv. So we take g from here to here by using one of the axioms of a star module. Now g becomes g bar, because the involution in COX is the complex conjugation. And by our construction of mu, this is the integral of f g bar with respect to mu. Or equivalently, this is just the inner product of f and g in the L2 space. The usual L2 inner product. So in particular, this chain of equalities shows that we have the following equality. The norm of fv equals the L2 norm of the equivalence class of f. If we substitute g equals f here, then we get this formula. So this formula implies that we have a well-defined map, a well-defined linear map, that's denoted by phi 0, from E to H, which takes the equivalence class of each continuous function to the vector fv. Well, indeed, this is well defined, because if f is such that this equivalence class is 0, that is, f is vanishes almost everywhere, then this equality shows that fv is also 0. And so this is well defined. And moreover, it's clear from the construction that phi 0 is a COX module morphism. Phi 0 is a COX module morphism. Also, its image is dense. The image of phi 0 is dense in H because the closure of the image is exactly the cyclic submodule generated by V, but we assume that V is a cyclic vector. So the image is dense. And if we look now at this formula again, we see that phi 0 preserves the inner product. Phi 0 preserves the inner product. In particular, it is isometric. So we can extend it by continuity to the whole L2 space. Well, E is dense in L2. So phi 0 uniquely extends to unitary isomorphism. To a unitary isomorphism between L2 and H. And this completes the proof. Okay, let's now deduce an operator theoretic corollary of this result, namely the functional model for star cyclic operators. So let's now recall an important result from the previous lecture. Namely, suppose now that T is a normal operator on the Hilbert space H. And suppose that K is a compact subset of the complex plane which contains the spectrum of T. We know from the previous lecture that T has a continuous functional calculus, gamma T. This is a star homomorphism, a unit of star homomorphism from the algebra of continuous functions on K to B of H. Continuous functional calculus. And let's also recall the standard notation. If f is a continuous function, then we denote the image of f under this homomorphism by f of t. In particular, if f is a polynomial, then this is indeed f of t in the usual sense. Just substitute t in this polynomial. So this homomorphism enables us to consider H as a star module over C of K. So H becomes a star module over C of K. And in fact, we get one-to-one correspondence between the collection of all normal operators whose spectrum is contained in K, and the collection of all star modules over C of K, or equivalently star representations of C of K. Well, indeed, the left to right arrow follows from the continuous functional calculus. Namely, T corresponds to gamma T. And the right to left arrow is almost trivial. Namely, if pi is a star representation of this form, then the respective operator is just P of little t, where little t is the inclusion map of K into the complex plane. Well, why is it one-to-one? Basically, this is an equivalent form of the uniqueness of the functional calculus. So in the previous lecture, we proved that if a functional calculus exists, then it is unique. In other words, if two representations of this algebra give the same operator, pi of t, then they are the same. Okay, so this operator theoretic, this representation theoretic interpretation of normal operators turns out to be very useful. Okay, so let's now look at operators which correspond to, I use this part of the board. So let's now look at the operators which correspond to cyclic star modules. We give the following definition. If we have a bounded linear operator T on the Hilbert space H, then we say that T is star cyclic. Actually, it will be convenient to give two definitions. So definition one, we say that T is star cyclic if there exists a vector v in H such that the following vector subspace, namely the closure of the linear span of all elements of the following form, where n and m are non-negative integers. So the closure of this subspace equals H. By the way, observe that this subspace is nothing but the smallest closed subspace, which is invariant with respect to both T and T star, provided that T is normal. But anyway, at this point, I don't assume that T is normal. So this is just the definition of a star cyclic operator. And we say that T is cyclic if there exists a vector v in H such that the linear span of all elements of the form T to the power nv, where n is a negative integer, equals H. And each such vector v is called a star cyclic vector, or respectively cyclic vector. For the operator T. Okay. So we have the following simple result, proposition. So suppose that T is a normal operator on a Hilbert space H, and K is a compact subset of the complex plane, which contains the spectrum. So that H becomes a C of K module. It's a star module over C of K. By means of this correspondence. So I claim that H is cyclic if and only if T is star cyclic. The proof is again a simple application of the Stone-Weierstrass theorem. Namely, if we look at the subalgebra of C of K generated by the function which is identically 1, T, where T is the inclusion map of K into C, and the complex conjugate, T bar, then this subalgebra is dense in C of K. We already used this argument when we proved the the uniqueness of the functional calculus. This follows from the Stone-Weierstrass theorem. And this observation implies that this subspace here, this closed linear span, where n and m run over all non-negative integers. So this closed linear span is nothing but the cyclic submodule generated by V. If T is 0,
Yes.
well, if T is 0, then it can be cyclic only if the space is 0. Because, well.
Yes, but
Sorry. If and only if the space is one-dimensional, because we can put if n is 0 and m is 0, then this is the identity map.
okay.
So the identity map is always in here. So V is always in this, V always belongs to this subspace. So we see that, this subspace is nothing but the cyclic submodule generated by V. So this follows from the density of this subalgebra in C of K. So in other words, each continuous function, f, can be uniformly approximated by polynomials in T and T bar. And so each vector of this form can be approximated by linear combinations of vectors of this form. And so when we take the closure of the linear span, these subspaces are equal. So in other words, this subspace equals H, if and only if this subspace equals H, which means exactly that H is a cyclic module. So this completes the proof. It's clear from the definition that if T is self-adjoint, then it is cyclic if and only if it is star cyclic. It's clear from the definition. By the way, there is another important result due to Brehm, which tells us that, in fact, this is true for all normal operators. It's 1955. If T is normal and star cyclic, then it is cyclic. But we will not use this fact. In fact, the proof is not so much functional analysis as general topology. Okay. Let's now look at, again, to this correspondence. And suppose that we have two star modules which are unitarily isomorphic. So we have the following very simple proposition. Suppose that we have two normal operators, S and T, two normal operators, and a compact subset of the complex plane, which contains both the spectrum of T, or the spectrum of S, and the spectrum of T, so that both H1 and H2 become C of K modules. Star modules over C of K. So I claim that if U is a C of K module morphism, then U intertwines S and T in the sense that the following formula holds. So in particular, this result shows that if H1 and H2 are unitarily isomorphic as C of K modules, then S and T are unitarily equivalent. So the definition of unitary equivalence between S and T means exactly that there is a unitary operator which intertwines S and T in the sense that this formula holds. The proof is almost trivial. So since U is a C of K module morphism, we have in particular the following identity, where little t is as usual the inclusion map of K into the complex plane. So now let's observe that this coordinate little t acts on H1 as the operator S. So this is U S V. And the same function t acts on H2, so this is an element in H2. So little t acts on H2 as the operator big T. And that's it. So this means that US equals GU. In fact, again, I state this without proof, that the converse is also true. But this is not entirely trivial. This follows from a deep theorem due to Faglit and Putnam. And as a simple exercise, I recommend you to show that the converse is true provided that S and T are self-adjoint. Okay, we now combine our previous results. Well, first of all, before we do it, let's look at a typical example of a star cyclic operator. Suppose that K is a compact subset of the complex plane, and mu is a positive Radon measure on K. And let's denote by MT the multiplication operator on the big L2 space on K, which is the multiplication by the coordinate. So it's easy to see that MT is,
maybe TF.
well, little t is, if Z is the point on K, Z is a complex number, and T is a function which takes Z to itself. T is the inclusion map. So T of Z equals Z. That's the difference. Z is a number and T is a function, which is just the coordinate. So Z is the argument of the function. And T is some special symbol which we use for this concrete function. So clearly this operator is normal. MT is normal because the joint operator is the multiplication by the complex conjugate function. And we obviously compute. And MT is star cyclic. Namely, the function which is identically 1 is a star cyclic vector. This follows immediately from the definition of a star cyclic operator, because the subspace, before we take a closure, if we look at the subspace in the first line, before we take a closure, this subspace will be just the space of all polynomials in T and T bar, which is dense in the algebra of continuous functions, and the algebra of continuous functions is dense in L2. So the closure is the whole L2 space, and so this is a star cyclic vector. And now we have the following result, Theorem 2. This is the functional module for star cyclic normal operators. Suppose that T is a normal star cyclic operator on the Hilbert space H. Then there exists a positive Radon measure mu on the spectrum of T. such that T is unitarily equivalent to the multiplication operator, MT, acting on the respective L2 space. So in view of our previous results, this theorem is just a special case of Theorem One. Namely, we take our operator T, we consider the continuous functional calculus for T, which equips H with a star module structure over the algebra of continuous functions on the spectrum. And we just apply, so by the first proposition, the respective module will be cyclic. So we can apply Theorem 1 to this module, and we get the required isomorphism between H and L2. And this isomorphism gives us a unitary equivalence between the operator T and the multiplication operator MT. Okay. So our next goal is to extend this functional model to arbitrary normal operators, which are not necessarily star cyclic. We'll need the following simple construction. Suppose that Hi is a family of Hilbert spaces. Family of Hilbert spaces. We denote by H the set of those elements in their product, Xi, in their product, such that the following sum is finite. So what does it mean? If I is countable, then it's clear what it means. But in the general case, we define this sum to be the supremum of finite sums. The supremum is taken over all finite subsets of I. We have the following simple exercise. First of all, if we take an element x in H, then this condition implies that xi vanish for all but countably many indices. In other words, each such element in this product is supported on a countable set. And exercise 2, H is not just a set. H is a vector subspace in the product. Is a vector subspace of the product. And it is actually a Hilbert space. With respect to the following inner product. The inner product of x and y is given as the sum of the following series. So now we look at this expression as a series, an actual series, because we already know that x and y are supported on countable sets. So actually this is countable sum. So we see that each collection of Hilbert spaces gives us a new Hilbert space, H, which is called the Hilbert direct sum. This H is denoted like this. So I put a dot here over the direct sum sign in order to distinguish between this space and the algebraic direct sum. And this is called the Hilbert direct sum. Of the family HI. Or sometimes we just say the Hilbert sum. Usually this doesn't lead to any confusion. Okay. So this is our construction. Let's now observe that this construction applies to star modules as well. So first of all, let's observe that if HI is a family of star modules, or unit-Banach algebra, unit-Banach star algebra, then H, their Hilbert direct sum, also becomes a star module over A. H is also a star module over A. Namely, the algebra A acts on each coordinate separately. The action is given by the following formula. So in other words, the Hilbert direct sum of a family of star modules is again a star module. And let's also observe the following. So we now look at a reasonable condition which will enable us to identify a given star module with a Hilbert sum of its closed submodules. So suppose that we have a star module, say H prime is a star module over A. And suppose that HI is a family of closed pairwise orthogonal submodules. Of H such that their algebraic sum is dense in H. So let's look now at the following map, as denoted by phi 0. So this is the map from the algebraic direct sum. So I don't put a dot here, meaning that this is the algebraic direct sum to H. So phi 0 takes each such family. So an element of the algebraic direct sum is a finite family of vectors. It takes xi to their sum. And this map, first of all, is an A-module morphism. Second, its image is dense, because its image is nothing but the closure of the algebraic sum. And finally, phi 0 preserves the inner product. this follows from the fact, from the assumption that the submodules are pairwise orthogonal. So this implies that phi 0 uniquely extends to a unitary isomorphism between the Hilbert direct sum uniquely extends to a unitary isomorphism between the Hilbert direct sum of our family and the module H. So in other words, if we have a star module and such a family of closed pairwise orthogonal submodules such that the algebraic sum is dense, then we have this unitary isomorphism. Okay. Essentially that's all for today. I'll just tell you the strategy of what we are going to do next. So we want to construct a functional model for an arbitrary that is not necessarily star cyclic operator. And again, we will work in the context of representation. So we start with a star module over C of x. So we are at this point we are interested in modules over the algebra of continuous functions. So we take a compact Hausdorff topological space, and we take an arbitrary star module over C of x. So our strategy will be the following. First of all, we decompose this module into a family of cyclic submodules, of pairwise orthogonal cyclic submodules. This will be step one. And then we apply our theorem one to each of the summands. So our module will be isomorphic to a Hilbert sum of the modules of the form L2 of x mu I, probably for different measures mu I. And then in some sense, we will combine these pieces together. We have many copies of the big L2 space corresponding to different measures. And in some sense, we combine these pieces together, and we get a big measure space, not necessarily finite, and a function, a measurable function on this space, such that our module will be unitarily isomorphic to the module which was described in our example 2. That is to the module of the form L2 omega mu phi. This will be essentially the general form of a star module over a commutative C-star algebra. And as a corollary of this result, we will get a functional model for normal operators on the Hilbert space. Okay, thank you. So that's all for today.